I failed to close the recording, and so I have to do it at home now. Okay, let's take over when we were at the proof of this theorem 2.2. If G is a tree, then epsilon is equal to ni minus 1. That is, the number of edges is 1 less than the number of vertices in a tree. The induction is on the number of vertices. With ni equal to 1, so just one vertex, then necessarily you don't have any edges, because you would, if you had a loop, that would be a cycle, and so the graph would not be a cyclic, and it would not be a tree. So there is no edge, and epsilon equals 0, which is exactly ni minus 1. The induction step is a bit different from usual, because generally we adopt as an inductive hypothesis the fact that what we are going to prove is valid for, in this case would be for ni minus 1. On the contrary, here we assume that the statement is true for any tree with less than ni vertices. Okay? Okay, so let's assume that G is a tree with at least 2 vertices, ni greater than or 2. Then take any edge of the tree. Let it be the edge between vertices u and v. Then, if you take away this edge, you don't have any uv path. Why? Because that edge is the unique path from u to v. We saw before that between 2 vertices in a tree there is exactly one path, and this path between u and v is that single edge. So if you take away that edge, you have no uv path, and so the graph G minus this edge becomes disconnected. And as you can see from exercise 1.6.8a, when you take away just one edge, the increase in the number of components is just by 1. So out of one component of G, you get 2 components of G minus UV. Okay? What can we say about these 2 components? They are connected and they are acyclic. Why? Because if G1, either with G1 or G2 had a cycle, that cycle would also exist in the original G, which is not, because G is assumed to be a tree. So they are trees. G1 and G2 are trees, and each has fewer than ni vertices. So what can we say? That epsilon of G1 equals ni of G1 minus 1, epsilon of G2 is equals ni of G2 minus 1. So if we want to compute again epsilon of G, we can see that it is, and that is also on the blackboard, it is epsilon of G1 plus epsilon of G2 plus 1, because we also have to add back the edge we deleted before. Okay? And so epsilon of G1 is ni of G1 minus 1, epsilon of G2 is ni of G2 minus 1 plus 1, and so minus 1 and plus 1 get simplified, and we get ni of G1 plus ni of G2 minus 1. But remember that by deleting that particular edge, we did not delete any vertices. So actually, ni of G1 plus ni of G2 equals ni of G. And so we get epsilon of G equals ni of G minus 1. Okay? Next, what can we deduce from that? We can deduce that every non-trivial tree has at least 2 vertices of degree 1, maybe several more than that, and we can see here we have just a tree with with the exactly two vertices of degree 1. Here we have 3, here we have 3, here we have 4, here we have also again 4, and here we have 5. Okay? How can we have an idea of this? Just think of, as I do at the blackboard, of summing up all the degrees d of v1, d of v2, and d of vn, and assume that it's not true what we state in the corollary. That is, that the degree of v1 is greater than or equal to 2, same for degree of v2, same for the degree of vn. Then by summing up everything, we would get the sum of all degrees to be greater than or equal to 2 times n. But it's not true, because the sum of all degrees is equal to twice epsilon, which is twice n minus 2. So at least in 2 cases we must have that the degree is equal to 1. Okay? And we have an exercise here that every tree with exactly 2 vertices of degree 1 is a path. It's not an easy exercise. Try, but not longer than 10 minutes. This is even more difficult. 2.1.8. It's an interesting exercise, but it's long also to prove. But again, try to think of it 10-15 minutes at most. The center of G is a vertex U, such that the maximum of the distance from U to V for V going through all of capital V is as small as possible. Show that the tree has either exactly one center or 2 adjacent centers. It's not easy to prove, but try. Let's go to things which are important for the idea of connectivity of a given graph. So take any graph G, and we call a cut edge an edge E, such that if you delete it, you get that the number of components of the graph without that edge is greater than the number of components of G. Please assume this as the true definition, but be careful, because generally we might have the temptation of saying an edge, cut edge, is an edge whose deletion makes the graph disconnected. It's not completely correct, even if it's the main idea under this concept. But actually, G might have from the beginning more than one component. It might be disconnected itself, and so you don't make it disconnected. It is already disconnected. What happens if you delete what is called a cut edge? It happens that the number of components increases, which is true also, of course, if G is connected. Omega of G is 1, omega of G minus C is 2. Okay. Theorem 2.3. An edge E of capital G is a cut edge of G if and only if E is contained in no cycle of G. I don't give the proof, but the thing is rather intuitive. That if you have a single bridge between 2 islands, then there is no cycle containing that bridge. But this is just one way of the if and only if. And so, as usual, one way is easy and intuitive, the other is much less intuitive and easy. But I don't give the proof anyway. Sorry. What is a spanning tree? We will talk in the next lecture about spanning trees a lot. A spanning tree is a spanning subgraph of G, which is a tree. What is a spanning subgraph? I recall it is a subgraph of G which reaches all of the vertices of G. So, a spanning tree is a tree which has all the same vertices of the original graph G. Every connected graph contains a spanning tree, and then as corollary, this is corollary 2.4.1, but then as a corollary 2.4.2, you get that if G is connected, then epsilon is greater than or equal to Ni minus 1. Why? Because being connected, you can apply corollary 2.4.1, and so there is inside a spanning tree, which is made of edges which are also edges of G. And so, since G in general has more than the edges of one of its spanning trees, then the number of edges is greater than or equal to the number of edges of the spanning tree, which is Ni minus 1. Consider that when we built all the paths from the privileged vertex in Dijkstra's algorithm, we got actually a spanning tree. And it will be the same with Kruskal's algorithm in next lecture, which means that you have the most economic connection, in that case from a particular vertex U0. It is the most economic because if you had two different paths from one vertex to another, then this would mean not the maximum economy. This would give anyway some redundancy, which can be safe for the network. So a spanning tree is at one extreme of the idea of finding a compromise, a trade-off between economy and safety. And it is the most economic, but it is the less safe. If you break one edge in a spanning tree, you lose connection. Okay. And here you can see depicted a spanning tree in a connected graph by the thickened lines. Now we have a sort of a generalization of the idea of cut edge, which is an edge cut. So let me start with this. Consider a set S of vertices and another set S prime of vertices. Then this symbol here, square bracket S comma S prime square bracket, means the set of edges with one end in S and the other in S prime. An edge cut of G is a subset of E of the form bracket is a square bracket S comma S bar square bracket, where S is a non-empty proper subset of V, and S bar is its complement. It's all the other vertices of V. By the way, a minimal non-empty edge cut of G is called a bond. And of course, in particular, if you have a cut edge, that gives you a bond. If G is connected, a bond of G is a minimal subset such that the deletion of the edges in B makes the graph disconnected. Here in the picture, you have on the left an edge cut. Here, these four on the left are the vertices of S, and here these four are the other vertices building so S bar, and you have thickened here all the edges connecting vertices of S to vertices of S bar. As was asked in class, this does not mean that this vertex is that this graph is bipartite. Why? Because there are also edges connecting vertices of the same subset. Okay. Clearly, in a bipartite graph, all edges build an edge cut. What's the difference with the picture on the right? It is that here the vertex sets are different. There are less edges, but this set of thickened edges is a subset of the one we have on the left of the picture. And we see that it's an edge cut itself, but with a different set of vertices. Here, the set S of vertices is the previous 4 plus this. And S bar is given by only these 3 vertices. And actually, if you take all the edges connecting the 5 on the of S with the 3 of S bar, you find these thickened lines. Since this is an edge cut, but it is a subset, a proper subset of this other edge cut, we have that the edge cut on the on the left is not a bond, while you can check by deleting one by one the edges on the right that if you delete some edges from this particular edge set, you do not get an edge set. So this is a minimal edge set and it is a bond. Finally, let's go to cut vertices. There is a sort of a leitmotif of a common thing that we do in graph theory. You find an interesting idea regarding edges, then you try it on vertices, and conversely, and you find a nice concept on vertices, you try to see what is the corresponding concept in terms of edges. In this case, we had the notion of cut edge. Let's see whether we can define a cut vertex. Well, be careful, because the definition, the true definition, is a bit tricky, and it is because of the possible existence of loops. If you have a loopless and non-trivial graph G, then you would define a cut vertex exactly in the same way as a cut edge is defined, meaning the deletion of that vertex makes the number of components increase. Okay, but it's not exactly so, because you might have loops, and I described that on the blackboard, meaning that if you have a loop at the vertex V, the deletion of vertex V means also the deletion of that loop, and so you are left again with only one component. So for a vertex at which you have a loop, it's not like what we had for cut edges. So the definition is broader in a sense and a little bit more cumbersome. It's like this. You define a vertex G, a vertex V of G, a cut vertex, if the set of edges can be partitioned into non-empty subsets E1 and E2, such that the graph induced by E1 and the graph induced by E2 have just vertex V in common. Okay, and it's exactly what you can see here on the blackboard. You have a graph G with a certain loop at edge at vertex V. Then you can divide the set of edges into two sets. One contains only the loop, and the other one contains all the other edges. If you take the two graphs induced by E1 on one side and E2 on the other side, you'd find two non-empty graphs whose only a common vertex is exactly V. And so this makes also in this case V a cut vertex. But don't worry, if you give me this other as a definition, I won't reject you for that. I will just comment that this is not totally general and try to get from you the correct general definition. Okay, so that's all for this lecture. See you.